Okay, great. Well then, allow me to introduce our next speaker, Quentin Merigot, who is a professor at the University of Paris-Saclay, and who will be speaking on the non-convex uniform optimal quantization problem. Thank you very much.
Okay. Okay, well, thank you very much for the introduction and also for the invitation. I apologize for not being here in person, but it was difficult. Okay, so I'm going to talk about a joint work with Filippo Santambrogio and Clément Sarrazin about uniform optimal quantization. So this is motivated. I will start with a standard optimal quantization problem, which is a very well-known problem in computer science and applied mathematics. So basically, you are given a probability density over a domain. Think of a convex set. Omega is a convex subset of Rd. And you would like to approximate this probability density with atoms, like Dirac masses, and with a convex combination of Dirac masses, like here. And you are optimizing both on the position of the atoms, but also on the masses of each atom. Okay, so here's a picture. There is a famous algorithm that tries to solve this. It's a difficult non-convex optimization problem, so it's just find local minimizer if you want. It's called the Lloyd's algorithm. It was introduced in the 80s. And basically what you are doing is the following. At every step, you compute a Voronoi diagram, which means that you decompose your open set into what are called Voronoi cells. So these are these sets here. And the Voronoi cell of the point Y3 is a set of points in your domain that are closer to Y3 than to any other point in the domain. So first you do this, and then you compute the barycenters of these sets, the Voronoi cells, weighted by the density. And then you move the points towards their barycenter, and you repeat. So this is an iterative algorithm. And you can show that if you do so, then you decrease the energy. So you decrease this quantity. I'm looking at everything as a function of yi, yn. So you decrease the energy, and the fixed points of this algorithm are critical points of this energy, again, as a function of yi, y1, yn. So this is an algorithm that's used and studied a lot in the computer science. It's also known under the name of k-means, when rho is not a density, but also discretely, finitely supported measure. And in computer science, people have in mind the limit where n is very small, like maybe 10, because you are trying to cluster data. You have a data set, and the data set that represents several classes, and you would like to split it corresponding to the classes, but the number of classes is not too high. It will be a few units. And it has also attracted the attention of mathematicians, for instance, but rather in the setting where n is very large. And so, for instance, one quite old result of Fejestos says that in dimension 2, if you look at the Voronoi cells corresponding to the minimizers of this problem, then they tend to be shaped like hexagons. As n goes to infinity, they look more and more like hexagons. And there is also more recent work, especially the thesis of Michaela, on the behavior of Lloyd's algorithm, which is reinterpreted in the limit n goes to infinity to a PDE, a fast diffusion PDE. Okay, so this is the optimal quantization problem, which I will not be looking at so much. In my case, we look at optimal uniform quantization. And this means that the alpha I, the mass in front of each Dirac, is not free. It's fixed to 1 over n. You look at uniform point clouds. And the first time I saw this problem was in an article in Computer Graphics by De Goos and some co-authors, where they were trying to approximate pictures using dots. And basically, the idea that you want the number of dots in a region to be proportional to the density of the image in this region, assuming that you have a grayscale image. And this is why you want to impose that each direct mass has a mass of 1 over n, not like the optimal quantization problem where the mass was 3. Okay. And it has also been looked at in the setting of optimal location problems by Born, Schmitzer, and Wirtz, but also for generating polycrystalline microstructures. So there are a bunch of applications, and I think also it's a very natural problem. Okay, so let me state a few other motivations before going to the results. So again, I'm looking at the compact convex sets. I'm looking at the space of probability measure over this space. I will use the Wasserstein distances that have been introduced in the previous talk. And I just want to mention a problem that occurs in machine learning, which is a problem of generative modeling. So you have some data set rho. So I approximated by your probability density, but it's just a huge number of data, a huge number of images, for instance, embedded in a very high dimensional space. And what you would like to do is to find some parameters, theta, so that generated data, so this is mu theta, is as close as possible to your real data. So you want to parameterize some neural network so that its result is as close as possible to some fixed probability density rho. And this is measured by the Wasserstein distance. Okay, so this is a very, very difficult problem. It's actually, I write it as an optimization problem, but it's more a minimax problem using the definition of Wasserstein 1 as a Cantor-Ridge Rubinstein duality as a maximum. So it's a difficult non-convex optimization problem. And one of the source of difficulty is, it's especially the case when what I want to say is that the Wasserstein distance is convex on the space of measures, but if you parameterize your measures and you move the support, then it's not convex anymore. And this is one of the sources of non-convexity in this problem. Okay, so what I'm looking at is, again, at uniform optimal quantization, and you can think of it as a variant of this problem, where you just parameterize the position of the atoms. So it's very simple to state. You have a finite set of points, and you want to minimize the Wasserstein distance between your density and a uniform measure over your points yi, yn. And in practice, if you try to solve this problem using gradient descent, you will see that it works pretty well, even if this problem is non-convex. And the aim of this talk is to explain this phenomenon. So the question is, well, does gradient descent lead to low configuration energies? Low energy configuration. Okay, so the Wasserstein distance is exactly the one you're used to. You're trying to minimize over all coupling the integral of the transport cost, which is a squared Euclidean distance. And in this uniform quantization problem, you can write it, you can see it's a problem which I would call semi-discrete, in the sense that this half is a discrete finitely supported measure, and this one is uniform, is absolutely continuous with respect to Lebesgue. And for semi-discrete problems, you can use Cantor-Ridge duality to get a more tractable formula for Fn. So here I'm just using standard Cantor-Ridge duality, saying that the minimizing the transport cost is equivalent to maximizing the integral of some Cantor-Ridge potential plus the integral of its C transform. And here, the C transform is quite simple because it's just a minimum over a finite set. So you can decompose omega depending on where the minimum is attained. And if you do so, you end up with a decomposition of the space, which is called a Laguerre tessellation. So said otherwise, you can write this integral here as a sum of integrals which are arranged over the Laguerre cells Lagi of y phi, and which correspond to where the minimum is attained. Okay. And maybe one last word is that the Laguerre cells, if you look at this definition, they seem not so nice, but actually you can expand the square norm and the squared x disappears. And so you can see that there are plain convex polyhedra in RD. Okay. And still about this optimization problem, this maximization problem, if you are given, if your points in the support are distinct from each other, then the maximizer of this problem is unique up to an additive constant, and it satisfies the first order condition that all Laguerre cells have exactly the same mass, 1/n. Okay. So now let me say a few words about the optimal quantization energy, which maps n-tuple of points to the Wasserstein distance between the uniform measure over these points and rho. And I would like to underline again that even though Wasserstein squared is convex, Fn is not convex. And actually, you can prove that Fn is a semi-concave, and that it is C1 on a dense open set. And this set is just the set of points of n-tuples where no 2 points are equal, are at the same position. And then you have a very simple expression. If you denote Fy to be the maximizer in your dual problem, Cantor-Rovich problem, then it's just the sum of the second moment of the Laguerre cells from the yi. So it's just the sum over each Laguerre cell of the integral of x minus yi squared, 0 of x. Okay, so let me illustrate this. So you have a point cloud which is displayed here. Then you can compute the optimal Laguerre diagram. It's done just by concave maximization. And you can see that each of the Laguerre cells here, they are in colors. They have the same mass. And then if you want to compute the gradient of this Fn, this optimal quantization energy, it just actually, it's yi, so a point, minus its barycenter. So this means that if you want to increase the energy, you would like to go away from the barycenters. But more interestingly, if you would like to decrease the quantization energy, you would like to move towards the barycenter. And if you look at this picture, it's quite conceivable that moving all points to the barycenter of their Laguerre cell, which will lead to a much better configuration. Okay, so let me summarize. So we have seen already Lloyd's algorithm, which works for optimal quantization of a density. First, you compute the Voronoi cells, which are equivalent to the Laguerre cells, but with phi equal to 0. And you move each point yi to the barycenter of the cell, and you repeat. Then you can look at a uniform version of this algorithm, which is very similar. You compute the Laguerre cells of each point corresponding where phi I is the solution to the optimal transport problem. So you look at the Laguerre cells that solve the optimal transport problem. You compute that barycenter, their barycenter, and then you move the point toward the barycenter. So these two algorithms, there are fixed point algorithms for cancelling either the gradient of the uniform the quantization energy or the gradient of the uniform quantization energy. It's easy to show that the iterates converge at two sequence to a critical point of these energies. But in both cases, there may exist critical points with high energy. Okay, so what do I mean by low and high energy? I will be a bit more precise now. So I'm looking for this estimate. I'm just looking at a density which is bounded from above and below on a bounded convex set. Then you can show that the minimum of the energy is within a constant times 1/n to the 2/d and another constant times 1/n to the 2/d. So this is what this theta notation means. It's borrowed from computer science. So the minimizers for this energy, they are critical points. Obviously, they satisfy the first order condition saying that every point lies at the barycenter of the Laguerre cell. But because this problem is non-convex, there exists critical points. No, there may exist some critical points which are not minimizers. So one very simple example is this one. So your domain is just a square. your density is just constant equal to 1, and you put the points in a straight line, then if you draw the Voronoi cells, actually you will see that they all have the same mass. So actually there are Laguerre cells which solve the optimal transport problem. And their barycenters, they agree with the point. So if you launch Lloyd's algorithm from this configuration, then it remains fixed, it doesn't move at all. While if you look at the energy of this critical point, it's close to 1. So it's very high. Okay. So experimentally, if you choose why the point cloud not in an adverse way, you can observe that just running once Lloyd's algorithm, so you just replace the points by their barycenter, then you get an energy that goes to 0 as n goes to infinity. So this is a simple example of this setting, and basically we would like to explain this. And this is what we get. It's a quantitative explanation. So we are looking at again at a probability density over some domain omega, which is convex. And I look at a point cloud in omega, and I assume that all the points in this cloud are far from each other. And this is measured by this exponent, which I will tell a word about it later. And if this is the case, then you can show that the Wasserstein distance between the uniform measure over the barycenter and rho is small. And this is again measured by another exponent. Okay, so what is this first exponent here? It's a way to measure, if you think of your point cloud Y, what is its dimension in some sense? So if Y was sampled evenly from a K subdimensional manifold, then you could expect that this quantity would be 1 over n to the 1 over k. So basically, this measures the dimension of your point cloud. And if the dimension is greater than d minus 1, then this is greater than 1. And sorry, this is smaller than 1, so this is negative. And so this Wasserstein distance goes to 0. And actually, you cannot expect to have this behavior if beta is equal to d minus 1. And this is easy to see. If you take a point cloud which is constant, so if you are working, for instance, in 3D on a cube, you look at a 2D square which is parallel to the axis, and you take any point cloud in it, then you can realize that the optimal transport actually will not move the points outside of the square. So if you run Lloyd's algorithm, you will always remain in the square, and so you can lower bound the Wasserstein distance by 1 over 12. So you cannot expect to improve this, to have convergence if beta is equal to d minus 1 or less than equal to d minus 1. When beta is equal to d, so this means when your point cloud is evenly sampled in the space, the upper bound on the theorem is 1 over n to the 1 over d. It's a simple computation. And if you recall what I told you, it does not match the upper bound on the minimum. So the minimum we showed that it was less than 1 over n to the 2 over d. We could hope to get 2 over d here, but actually it's not the case. And we can show that the exponent in this upper bound, here, cannot be improved. Okay, so I will show this briefly. So how did we come to this? Actually, we notice this phenomenon looking at the Gaussians. So if you look at the Gaussian density, the value of the density at the boundary will be close to 0. And if you run Lloyd's algorithm from a random situation, it works pretty well. But if you run Lloyd's algorithm, but starting from a grid, you reach a fixed point of Lloyd's algorithm. You reach a critical point in one step. And this critical point is not so nice. And actually, if you show the energy, the uniform quantization energy, the Wasserstein distance, squared Wasserstein distance, as a function of the number of points. For a random initialization, you get n to the -1, and for a grid-like initialization, you get n to the minus 0.78. Okay, and actually, you can construct a simple example where showing that this bond is tight. Okay, I skip it because I'm out of time. Okay, so last numerical example, which I find nice, it's with an exponent that is between d and d-1. And to do that, I just sample a fun core fractal, a fun core snowflake. And this is before the initialization. And we compute the Lagarde diagram. We move the points to the barycenters, and this is what we get. And if we increase the number of atoms, we can see that it samples well the space. And numerically, it seems that the exponent is n to the -1, whereas we predict an exponent of -0.2. So there is still room for improvement. Okay. Okay, so I think I was ambitious in what I wanted to tell you. So I will just move to the conclusion. Okay. And okay. Yes. So basically, what we showed in this talk is, despite the non-convexity, gradient descent strategy for the optimal uniform quantization problem, they work well, assuming that the initial points are far from each other. And there are many open questions, and this is maybe what I want to insist on with this talk, is that we can wonder whether a lot of things that are not known. So we have this example showing that if the density can go to 0, then the exponent is tight. But what happens if the density is bounded from above and below? What happens if the density is supported not on RD, but on a submanifold, which I think from the point of view of application is quite important. What can we say about the limits of discrete critical points? What do they converge to? And finally, what about stable critical points? So I think I will stop here, and thank you for your attention.
Thank you very much, Kata. Are there any questions? And also, please, the Zoom participants should also not be shy to ask questions. Either I can attempt to read if you type in the chat, or you can just unmute yourself and speak. Yes. Okay.
Yeah, so when the dimension condition is not satisfied, then can we somehow characterize the limit as n goes to infinity?
So sorry, I have to switch to the room. I don't see you, sir. Sorry, can you repeat?
Okay, so
And yeah, I think unfortunately you're seated a little far from the microphone here. I'll bring you the, yeah, it's also hard with the mask. It's like it makes us more quiet. Here you go.
so when the dimensionality condition you mentioned is not satisfied, then can you characterize the limit as capital N goes to infinity?
So when the condition on the dimension is not satisfied, you mean when beta is less than d-1?
Yeah, right. Like
Yeah.
with like.
Yeah, so in this setting, actually, we can show by example that there are some cases where you don't get convergence. I mean that you have a lower bound, which is a constant between your limit, your barycenters and the rho. So it does not converge to 0 as n goes to plus infinity.
Okay, I see. Thank you.
Yeah.
I could try to talk. Can you hear me?
Yeah.
Right.
Yes.
I have a question concerning the computation of the Laguerre cells. You were describing some connection, for example, to these generative networks and stuff. Is actually feasible to compute the Laguerre cells when the dimension is very high? Because your examples were all dimension 2 and 3, so.
Yes. Okay, no, I agree, definitely. For high dimension, it's perhaps doable. It's not completely out of reach if n is not too large, because you can use stochastic techniques. So for instance, Aude, Genvet, and some other people did that, but it's still not very realistic. So I think in high dimension, people just use Kantorovich-Rubinstein formula, and actually they don't look at all the one Lipschitz function. they look at a subset that are generated by some other neural network. So in practice, it's not what people do. But I like the 2D and 3D case, actually, the application to images and so on. So
yeah, right. I actually prefer, I mean, this approach you're explaining here is very nice. That would be very nice if people would be able to compute in high dimension, because of course, this reduction to neural network for the dual formula, I mean, it's, I don't know, not directly like a proper theoretical result or whatever. I mean, yeah, but I heard that it was hard to compute. Thank you.
thank you.
Any other questions?
So can you hear me, Kantan?
Yes.
Okay. So the question was about the constant doesn't depend on rho.
Mm-hmm.
So it depends only on the.
No, actually, the cost. Yes, this is a good point. The constant do not depend on rho, and they do not depend actually on rho being a density. So I'm just stating the results in terms of density, because if not, I have to define what are the Laguerre cells. It's a bit more annoying, but actually everything holds, even if rho is supported on a, well, it's any measure supported on omega.
So my question was how this. So of course this is can be seen in a way, right, as a way to sample from rho. Right, so you take a uniform measure, you sample from a uniform measure, and then you take this one step, and you're basically almost optimally sampling from rho, right? Because only the exponent is changing. How does this relate to the sampling algorithms?
Okay, so in terms of sampling, if you compare to what you get just by random sampling, if you're able to sample randomly from rho, then actually it's much worse what we do. Okay. So I think the main field of application for this type of techniques is when you have some sort of inverse problem. So this is what I showed you maybe in the, let me try to go back. So I need to go to the beginning. For these generative models, if you have some inverse problem where so this one here, you would like to find some transformation of a measure or a parameterized measure which is close to rho, then you can use these techniques and it makes sense. And it could be a low dimensional problem. But if you just want to sample from rho, then the best is to do random sampling, you get a better bound. Okay, so if you do random sampling, basically you for high dimension, for d larger than 3, I think you get sorry, you get this as an error with high probability. So it's not competitive. It's more for inverse problem when you would like to use the Wasserstein distance as a loss function to measure the distance between your generated data and what you want to achieve, your real data.
Questions? Okay, if not, then let us thank Kata again. Thank you very much. And we now have a coffee break, and we'll resume at 10:45 a.m. with Antonio Esposito and Dan Chapcha.